Today's video will be on derivatives and rate of change. The rate of change of function f is represented by the slope of the tangent line. This is found by using the slope formula of change in y over change in x, so y2 minus y1 over x2 minus x1. As you can see, that's displacement over time, and this is the basic formula for finding the slope of a line. The instantaneous rate of change is used to find the rate of change at an exact point. As the displacement between 2 points on the tangent line diminishes, the displacement is getting closer and the rate of change is more exact. Therefore, the instantaneous rate of change is equal to the limit as x approaches 0 of f of x. This is equal to the derivative of f of x, which by the limit definition is the limit as x approaches 0 of f of x plus delta x minus f of x over delta x, which as you can see is the slope at that exact point, which equals the instantaneous rate of change. Now for part B, we have to find the instantaneous rate of change of f of x equals 7x squared minus 3. Note that this is a different function than part A, and it's at x equals 4. The instant rate of change of equals the derivative of x. So, by using the limit definition, you can find that the limit as delta x goes to 0 of f of x plus delta x minus f of x over delta x. Now, if x equals 4, you sub that in, and you can get that and with some equations, you'll get that the limit as delta x goes to 0 is 56 plus 7 delta x. Now, if delta x is 0, the answer is 56. Now, you can check this with the power rule for finding derivative. And remember, the derivative is equal to the instant rate of change. So, if you use the power rule, then the derivative of f of x equals 56, which is correct. Another type of problem you may see with derivatives and rate of change is when it asks you to find the equation of the tangent line to f of x. In example 2, we see that x equals 6 and the function equals the square root of x plus 2x. So, first you're going to want to find the instant rate of change since it's giving you an exact x value. Now the instant rate of change equals the derivative of that x value. By using the limit definition, we can find that the limit as delta x goes to 0 equals the square root of 6 plus delta x plus 2 times 6 plus delta x minus the square root of 6 plus 2 times 6 all over delta x. Now, once you simplify this, you're going to want to multiply by the conjugate to get rid of these square roots and so you can isolate delta x. By multiplying by the conjugate, you're going to get that the limit as delta x goes to 0 equals 18 plus 3 delta x minus 18 over delta x times the square root of 18 plus 3 delta x plus the square root of 18. Now, the plus 18 and negative 18 can cancel out, and the delta x on top can cancel out in the delta x in the denominator. This solves the problem of having delta x in the denominator, so as delta x goes to 0, it is no longer no solution. With some simplifying, you can find that the limit as delta x goes to 0 is equal to 3 over 6 root 2. Now you're going to want to move the root 2 to the numerator, so this is going to equal root 2 over 4, which equals the slope. Now, this answer is your instant rate of change at x equals 6, which equals to the derivative of that function at 6, which equals to the slope of your tangent line. Now, using the slope and the point 6 f of 6, which equals 6 root 18, you can solve for the equation of your tangent line, which is going to equal y minus root 18 equals root 2 over 4 times x minus 6. Now remember, a common mistake with these type of problems is solving for the slope, but forgetting that the question asks you to find the equation of the tangent line. Always remember to answer the question and put it with the equation. Using derivatives and rate of change is also useful when solving velocity problems. With this equation, the position of an object at t time is equal to 1/2 gt squared plus v naught t plus s naught. Now, The g represents the acceleration due to gravity, which equals negative 9.8 meters over second squared. The v naught equals the initial velocity, and the s naught equals the initial height. Now, this is the function that gives the position of an object as a function of time. So, when you want to find the average velocity of an object, you can use the average rate of change equation, which equals displacement over time. However, to find the velocity of an object at a specific time t, you're going to have to apply the instant rate of change, which is the derivative of that function. So, the derivative of the position function is going to equal the velocity. Now, the velocity at t time is going to equal, according to the limit definition, the limit as delta t goes to 0 as the position of t plus delta t minus the position of t all over delta t. This is using the limit definition, but you can also find the derivative of the function given by using power rule or product rule and shortcuts such as that. Now, rate of change can help solve problems about population growth, rates, production rates, water flow rates, velocity, and acceleration. Here's an example that deals with using the rate of change to find the velocity. This is adapted from www.ms.uky.edu. If the height of an object at t time, denoted as ht, is above the ground at time t, find the height when the velocity equals 0. With this function, h of t equals negative 16 t squared plus 96t plus 1. Now, the velocity, as we saw before, equals the derivative of this function, which is going to equal the instant rate of change, because it is the slope of that tangent line at the specific time. So we're going to need to find the height when the height equals the instant rate. We're going to need to find the height when the instant rate of change is equal to 0, as it asks in the question. The derivative of the function is going to equal the velocity of the function. So, using the limit definition to find that derivative, is going to be denoted as so. Once you simplify and cancel out the proper parts, you'll be left with a delta t that can be factored out, which can cancel with the delta t in the denominator. Once you do this, you know that the solution when you plug in 0 for delta t will not be undefined. This leaves you with negative 32t plus 96 as your velocity function for this object. Now, when you set this equal to 0 as it asked, you're going to find that t equals 3 seconds, which is going to be the time when Now that you have the time, you're going to need to find when the height equals that. So to do so, you're going to use that height function that it gave you and plug in 3 as t. So the height at 3 seconds is the height of 3, which is going to equal 145 feet. In addition, to get the instant rate of change, you do not have to use the limit definition. You can also solve for the derivative using the power rule. But in this case, we use the limit definition to show the derivative of that function.